So the next part of the program today is the award of the House Scholar for 2015. As many of you know, this award is made every year to one of the CSGF fellows who's graduated in a recent year. And it's made in the memory of Frederick Howes, who most of you know was a program manager at the Department of Energy and Oscar in the 1990s. Actually, Fred's background was as an applied mathematician. I first knew him when he was a professor at University of California at Davis. And we collaborated on developing methods, computational methods for multi-scale problems back in the 1980s. He was at Davis until I think the early 90s when he moved to this area to become a program manager at Oscar. He was highly respected and admired for his energy, dedication, and personal integrity, and it's for this that we honor his memory each year by awarding one and sometimes two House Scholar Awards here at this meeting. So it's my pleasure to make the award this year to Dr. Devin Matthews, who earned his PhD in chemistry from the University of Texas at Austin in 2014. After graduation, he joined the Institute for Computational Engineering and Sciences at the University of Texas at Austin, also as a postdoctoral fellow. His selection as a Howes Scholar reflects both his exceptional technical achievements as well as demonstrated leadership and character. And I'd like to read the citation for his award here. Devin's research is focused on the development of advanced algorithms and software for problems in quantum chemistry. Given the limitations of the experimental research at microscopic level, computation has become an essential part of quantum chemistry. Advancements in computational algorithms and tools are directly translated into our ability to understand and manipulate matter at the molecular level. By developing both algorithms and software of unprecedented precision and efficiency, Devin has made significant contributions to expanding the boundaries of computational quantum chemistry. Combining expertise in chemistry, computer science, and mathematics, he was able to create computational tools that enable electronic structure calculations with accuracy unattainable by previously developed packages. In addition, he spearheaded the development of the Aquarius framework, a comprehensive software infrastructure for tensor computations, particularly of the form encountered in quantum chemistry. The Aquarius software package provides the most advanced computational infrastructure for tensor calculations in terms of efficiency, different data types, parallelization, and software design. Devin's leadership in the initiation and development of this project speaks highly to his willingness to challenge the bounds of state-of-the-art in computation, to take responsibility and to follow through with dedication and drive. The computational tools he created are gaining wide recognition and are increasingly utilized by research groups throughout the field. Devin has also proven himself as a mentor for and a leader of his peers. Even as a graduate student, he took it upon himself to spur research projects, supervise, and help fellow graduate students and other colleagues. Devin is highly regarded by his fellow researchers for his integrity and character, as exemplified in his dedication to his family. Devin's demonstrated excellence in research and leadership in the computational quantum chemistry community exemplifies the qualities that Fred Howes encouraged in all young scientists. He serves as a role model to his peers and as an effective advocate for the field of computational science. Anyway, congratulations. Devin, if you would come up. And I'll be presenting the award, which consists of a crystal memento and a nice check. So let's stand where the photographer will be happy. I think that's we're good. Okay.
Thank you.
Congratulations.
Thank you very much.
Yeah,
So I'm really kind of surprised to be here and kind of overwhelmed that I would be chosen for this honor. And I just hope that in future years I can give the program and the community as much consideration and as much honor as I've been shown. So today, you heard mention of the program Aquarius, and that's what I'm going to be talking about today. And essentially what I'm talking about is what I have written here, fitting square pegs into round holes. And as you'll see, what that means is if you have two programs or pieces of code or interfaces or whatever, very rarely are those designed to work together. And even if they're designed to work together, very rarely do they actually work together very well in practice. So what I'll be talking about is making these things work together, whether they're designed to or not, essentially forcing these square pegs into the round holes. And we're also going to be playing a game. You all need to participate. We're going to be playing Spot the CSGFer. So if you see someone you recognize, just holler out. So to sort of set the stage, let's talk about sort of a typical calculation that I or one of my colleagues would do in computational chemistry. So there are a lot of steps here. First off, we have to start with what are called the atomic integrals. These are just sort of a big set of numbers that we come up with which would describe our molecular system. Then we have to do what's called the Hartree-Fock step. This gives us an approximate guess to the wave function of our system. Then we need to do an integral transformation. We take these guys, and we take this solution, and we put them together to make a new representation of our molecule, which is somewhat more accurate and which is easier to use. Then we do another calculation, which gives us more accuracy. And then we can take the wave function that we get in this step, and we can compute various things with it. We can optimize the geometry of a molecule. We can compute properties. We can compute spectra, all sorts of things. So at each level here, we have a bunch of different algorithms we can use, though. So for example, for the atomic integrals, we can use various letter soup combinations which do different things. And they all get the same answer in the end. But these could be different programs that are implementing these things. They could have different requirements in terms of memory usage, in terms of how parallelizable they are, all sorts of different things. And at the next layer, again, we have different algorithms. And these things can even be very different. For example, if this Cholesky or density fitting solver actually calculates the Fock matrix, which is sort of the central thing we're doing at this step, in a very, very different way from the other steps. And so you really have to make a choice. Which one am I going to do? And if you're writing a package to solve these things, you really have to pick, okay, which one am I actually going to implement? Because you don't have a lot of time to write these, to actually implement these codes. Again, for the integral transformation, we have various different algorithms which may have different properties in terms of parallelization, memory usage, and so on. Again, there are different methods for the correlated calculation, and many different options and algorithms for how to do these gradients and properties and things. So at every level, we have a choice of different algorithms, different techniques, perhaps different pieces of code to use. And so let's take an example of one sort of comprehensive computational chemistry code. It may standardize on, say, let's use the McMurky-Davison method here. Let's do an integral-driven Hartree-Fock. Let's do an out-of-core sequential integral transformation. Let's use this correlated calculation with this convergence acceleration and do something down here, okay? And so that's the code that they chose to write. That's what's in the package. And when you run the package, that's what you get. Let's say someone writes a different package, okay? They use a different integral algorithm. Let's say now they're using this fancy Cholesky Hartree-Fock solver, but the only correlated calculation that's been implemented, let's say, is MP2. So you have a more restricted range of calculations you can do down lower here in this graph. So we can do different things, maybe somewhat a set of overlapping things, but not really a set of compatible things. And maybe we have a third set. We do a different integral method. We have a different kind of Hartree-Fock. Maybe we have a distributed integral transformation, so this works well on larger scale systems. We do some fancy local methods here, but we don't have properties implemented for this. We don't have gradients and things like that. And so there are a lot of different pieces that are put into these different codes, but you can't put all the pieces together to get all the things you want. You can easily come up with combinations of things from here, 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 and here that simply don't exist in the codes as they're written now. So I'd like to take a moment to mention some work that's done by Dr. Lori Burns at Georgia Tech. She's actually been working on this in the context of two packages, the C4 package, which I do some work on, and the Psi4 package. And her canonical example is Psi can do DFT, but it can't do anharmonic force fields. C4 can do anharmonic force fields, but it can't do DFT. And so she's written code that can actually put these two together so you can do anharmonic force fields for DFT utilizing both packages. And that's kind of similar to some of the things I'll be talking about in sort of a more general way. So let's pick one of these classes of algorithms as a motivating example. And in my case, I'm going to pick tensor contraction. So what is tensor contraction? So it's essentially like matrix multiplication, which hopefully most of you are familiar with. But instead of matrices, which are flat, sort of two-dimensional objects, we can have a variety of dimensions, anywhere from 0 to infinity in integer increments. And so essentially, it's the same thing. We have some of the dimensions from A and some of the dimensions from B that we're going to multiply together and then sum. That's essentially the operation. However, there's no standard interface like there is in BLAS. You can't just call tensor dgem and it works. You have to often use handwritten algorithms to reduce this to something which you can do efficiently. And often this actually reduces to dgem, although it takes a lot of work to get there. And lastly, chemistry applications in particular take advantage of a lot of structures of these tensors. These come from, for example, spatial symmetry. So for example, look at the water molecule. It has several planes of symmetry. It has a symmetry axis here. And this induces some block sparse structure in these tensors, which you really have to take advantage of if you want to get the full efficiency of the calculation. So where do we use tensor calculations? So for me, I use these in coupled cluster. And what is coupled cluster? Well, it's some math. That's not really important. This is coupled cluster. This is what we do. But really, this is kind of misleading because this is really what chemists just do to look fancy. And if you take each one of these guys, all it is just an algebraic term. So each little picture is an algebraic term. In each algebraic term, if you look at here, we have some of the indices here, some of the indices here. We multiply them together, sum, that's a tensor contraction. So all coupled cluster is a sequence of tensor contractions. However, you'll notice we have varying numbers of indices. So for example, here we have 4 indices, here we have 6 indices. Sometimes we'll have 2, 8, 1, 3, whatever, lots of different numbers of them. And we're going to be contracting these together in lots of different ways. So here, we contract over these. Here, it's a different set, different set, different set. And so it's hard to simply take these tensors, these objects, and write them as something that we can directly use dgem on, that would be matrices, because the way that these mapped matrices keeps changing. So you really have to use actual tensor algorithms for these. And especially in the distributed case, in order to fully use the advantages of, for example, the hyper-torus networks of things like the Blue Gene Q, you actually have to treat all of these tensor dimensions as separate. So we really need, honest to God, tensor libraries to do these efficiently. So how do we actually write code to do this? So let's take this one very small example of this term here. So if you'll see, this guy has 4 lines coming out of him, so he's a 4-dimensional tensor. This guy has 4 lines coming out of him. He's a 4-dimensional tensor. And there are 2 lines left over. So this is a 4-dimensional tensor times a 4-dimensional tensor into a 2-dimensional tensor. This is one of the simplest tensor contractions we have in coupled cluster. So to write it in sort of the legacy approach, this is what you would find in a package like C4. It takes this much code plus lots more, probably about a factor of 4, maybe 5 more, just to implement this one term. And you'll also notice that this code doesn't have any MPI in it. This is sequential code. Now it can use, for example, multi-threaded BLAS, but to make this distributed parallel is a lot more code. And it does a lot of things the hard way. It does explicit indexing. It does lookups of the different sizes. It has to deal with permutational symmetry and transposing things to make them into matrices, all the stuff that has to do by hand for every single contraction. And so when you multiply this by several hundred, you get a lot of code. Now let's take a look at Aquarius. So this is Aquarius, some code here. This line, the purple line, is the previous slide, is that one diagram. And what happens here isn't really specified. This could be a sequential algorithm, it could be a distributed algorithm, it could be lots of things. It just simply does it. And this also takes into account all of the symmetries we had before and all of the sparsity. And the rest of the talk basically is explaining how is this possible. But one thing I'd like to mention before is that the code in the previous slide is written using a kind of interface. So all of the functions here, so a dgem, these functions to do transpose and things like that, see, these form an interface. So we write some code, it uses this interface, and so we have the code, we have the interface. Here we have the same thing. The interface is a much higher level. The interface perhaps is more expressive, all these different things, but it's still an interface. We have to write our code in a specific way to take advantage of what this code does. And so I guess what I'm really trying to say is that if you run this code today, you run this code tomorrow, it's going to do the exact same thing. What we want to do is we want to write our code once, and tomorrow have it do something completely different and take advantage of new properties of our computational systems, use new algorithms without changing our code. As an example, if we look at, I should mention here, you guys didn't yell out. This is Edgar Solomonic, who recently graduated. This is Jeff Hammond, who's in the back of the room somewhere, both former CSGF fellows. I worked with them at Argonne National Lab on my practicum a few years ago, and we sort of got together and started writing code, and Edgar wrote the distributed tensor library CTF, which is what is under the hood here, and takes care of everything here. As a counterexample, you might say, okay, well here's one interface for accomplishing this, but here's another interface. This is the libtensor interface, which is a very similar thing. And if you actually look, you can actually match up lines of code between the two. And they're essentially one for one doing the exact same thing. But the code that's written is not the same code. You can't take this code, compile it with libtensor, and it works. They have different interfaces. So even though they're accomplishing an extremely similar thing, they're not compatible. So we might say, okay, instead of having our code and it calls this interface, and this interface calls CTF or libtensor or whatever, let's have some code that under the hood can call a lot of different tensor libraries. Okay, so it could call CTF, it could call libtensor, it could call these various other things, and then we're happy, right? We can run on a variety of different systems. Some of these have different strengths and weaknesses. Libtensor is very good at large out-of-core calculations where you have a lot of disk space. CTF and some of these other ones are massively parallel. So this could be really good for us, right? However, if we do this, we're implicitly going to put biases and assumptions into our interfaces. So for example, let's say, now this isn't necessarily the truth, but let's say Aquarius depended on the data layout of our underlying tensor to be cyclic. So that would mean it could use this library and this library and this library, but maybe not the other ones. And then we have some other meta tensor library, some sort of higher order interface that maybe makes some other assumptions. So we can use this library and this library, and so on for this one. And now we're right back in the same spot. Our libraries are different enough that we've perpetuated our differences into this level. And so now if we want to be able to use all of these libraries interchangeably, we'd have to write yet another meta-meta tensor library or something like that. So of course this quickly becomes a problem. We have to write an interface that can take advantage of all of the features of these libraries without falling prey to their differences. And that's the hard part. And so my solution to this is what I call capabilities. So as I said, different libraries support different operations. at the core, they all support tensor contractions, but they do maybe do this in different ways. As I talked before about these special structures in chemistry, some of them support maybe one structure or a different structure, and if that support is there, you certainly want to take advantage of it and use it. But if it's not there, you want to be able to also use the capabilities that it does present. So you want to be able to take advantage of everything that's offered, but not be held back by stuff that's not offered. And so we classify everything that our tensor library can do by a set of capabilities. And so now our interface that we define needs to be flexible and modular, because each capability is going to be a component in this interface, and we have to be able to put them together seamlessly. Okay, so what would a generic flexible interface look like? So first of all, we define a collection of capabilities. We say our interface needs to do this, or our interface provides this, and that is defined by a collection of capabilities. Next, capabilities are hierarchical. One capability may imply another. If we're able to do X, then automatically we should be able to do Y. So they can be hierarchical. They can also be synergistic. If I have capability A and capability B, I can do certain things with A, I can do certain things with B. But wouldn't it be awesome if I had both of these things, I could do something new that I couldn't do before? And lastly, the interfaces are nested. And what I mean by this is that our tensor library is going to export some set of capabilities. These are the things that it knows how to do. But the code that is using this doesn't have to know every single one of those capabilities. It can just ignore some of them. Okay, let's say if our tensor library is distributed and supports access to local data and all sorts of different things that are only relevant to distributed computations. But our code doesn't really want to deal with that. It can just ignore all of that and still work seamlessly. So this is sort of the old way of writing code. So we have our code, we have implementation of some algorithm, usually in a library, and the code would simply call the implementation. That's how code is written, right? We have a code and we have the library. But no, we don't want to do that. What we want to do is we want to put an interface in between. And this may seem kind of like a no-duh kind of thing, because implementations, they have an interface, right? There's a set of functions that you can call, a set of variables that you can modify, et cetera. But that's not what I mean by interface. And actually, if you look closely, there are two interfaces here. There's an external interface, which is what the generic code uses. And there's an internal interface, which is what our implementation provides. And it's going from this interface to that interface, which requires this thing in the middle. And when we define this interface in terms of capabilities, we make it modular and flexible, we can actually automatically generate this interface here. So as long as this guy provides at least what this guy needs, this guy can make it happen. And that's where the real magic is. So let's just real quickly go through what do we actually need to make this happen in a language, say, like C++, which a lot of us are very familiar with. So we have, again, our three boxes. We have, well, actually, I've only drawn two boxes. The generic code is off somewhere to the left. So this is our implementation, and this is our interface. And as I said, the interface is automatically generated. And what that means in C++ is it's going to be a chain of templates, each template for a different capability. And so if we need a capability, this template's turned on. If we don't need a capability, it's turned off. And they're automatically strung together by the compiler. And then we go through a choke point here, which I'll get to in a second. We have another interface here, which works much the same way. And this bit here is the part that actually calls our external library, like CTF or libtensor or something. So on the left, this is automatically generated by the compiler. So all we have to do is define the pieces, and the compiler puts them together into a whole for us to use. We can use lots of template functions. We can do static checkling and have the compiler do all sorts of things for us. Then what we do is we pass through this middle point here. What we do here is we do what's called type erasure, which means that whatever this thing is, we ignore it. We call it void, something like that. And at the time we actually need to look up what it is we need to do, we can convert that back into what it really is. So we've taken this, we've genericized it, reduced it to just a lookup table that this guy can call. So no matter what's over here, all we have to do is go through this lookup table and we can get where we need to go. So this part can be completely swapped out. And then this guy is also automatically generated to a degree. But now we use things like virtual functions and runtime checking to complement what exists over here. So the actual code is a little bit more complicated. This is what I have on my whiteboard in my office to describe the actual class hierarchy. But in the end, it all works pretty well. And so, for example, here are some capabilities which are relevant to tensors. So as I said before, it may be distributed. So this means that we want to access only the local data for efficiency, or we want to have some control over the layout of the data, how the data is distributed. And so our library can expose those kinds of functions. Our library can also be indexable, which means that we can talk about individual indices of these things. Is it 4-dimensional? Is it 6-dimensional? Is it bounded? Can we access the data in some deterministic way? Does it have point group symmetry? Does it have index permutational symmetry? All these different kinds of things. And so using this set of capabilities, you can actually put together an interface which works. And so far, I've gotten it to work for self-consistent field theory and for the integral transformations, and I'm working on putting this together for the couple cluster as well. OK, so with that, I'd like to move into the second part of my talk, which takes what I've just talked about and makes it even more general. So this is what I call the marketplace. So let's say we're here. We're some guy trying to write some code. And let's think of it like shopping. We're going to go out shopping, but we're going to shop for algorithms. So we need someone that can do tensor algorithms. So we could go to Tensors R Us. We could go to Tensor Shack. We can shop around and find the algorithm that we need. And we need something else. We need some atomic integrals. We need a Fock builder. We need an iterative solver. We don't have to pick one piece of code and have that be the solution for all time. Even at runtime, we can go shop around and say, I need someone who implements interface X, and find the person who can do that the best job at the time. And so one time we run the code, OK, maybe we use one integral here, one algorithm here, different algorithm here, different algorithm here. We move to a higher scale. We move to different memory constraints. We need things in a different amount of time. And the algorithms here could change dynamically. And so now what we've done is you remember back at the beginning, we had all those little bubbles of algorithms. Each one of those now winds up as what I call a vendor in our marketplace. And so now, with each one of those encapsulated as a vendor in our marketplace, we can now string all those together in any way we want, at least any way that's theoretically compatible. And so now we don't have to standardize on one set of algorithms, on one piece of code. We can write our code to be generic and use any algorithm which is available to us at runtime. Of course, to decide which algorithm to use, we have to have some sort of metrics. And since we care about time, usually, we want to know how long would some calculation take using this particular vendor. We also want to know, for example, how much memory would this take? Does this fit in the memory we have available? If we use less memory, does it take longer? Questions like this. And so what we want is for our vendors to say, yeah, I can do this in 37 minutes with 1.4 gigabytes per processor. And if someone else can do it for less, then we pick him. So this allows us to efficiently shop around for the best algorithm. And so here's an example of some different pieces of the marketplace, some different vendors that are available for one of the steps we had earlier. This is the Hartree-Fock self-consistent field step. So we need to do several things. First of all, we need to build our Fock matrix. And as I said before, there are various different algorithms to do this. So what we do is we make these guys vendors in this market. And so at runtime, we choose which one we want to do. And of course, we could be open to hints from the user, hints from other pieces of the code as to which one is the most efficient, which one we want to do. If the user says, I want to do Cholesky, then we should do Cholesky, not the other ones. In turn, each one of these guys needs some atomic integrals. And so we have to go to the integral evaluator marketplace and pick one of these vendors to get an algorithm. Also, we need to diagonalize our matrix, so we need an eigensolver. So we can pick one of a variety of eigensolvers. Then, since a matrix is essentially a tensor, and we're working with tensors later anyway, so we might as well represent our matrix as a tensor, we need a tensor library. And so we need to go to the tensor library marketplace and pick a tensor library algorithm. And if you look also, there's this line here. The Cholesky algorithm actually represents pieces of the Fock matrix as higher dimensional tensors, as three-dimensional tensors. So this guy also needs a tensor library. And so you might worry, okay, what if this guy chooses one tensor library and this guy chooses another tensor library? But actually what you can do is this guy chooses a tensor library. When he's choosing this library, he can just tell him, oh, I already picked one, and he can pick the same one. But he doesn't have to. Actually, if this task, this vendor has different needs, which would necessitate a different tensor library, a different tensor library could do it better, it could pick a different one, and then it could convert. There's no problem doing that. So another thing we can do is that with capabilities, we can take advantage of all of the features of some library or algorithm while not being held back by certain libraries or algorithms deficiencies. But sometimes we really need something to happen. We really need some sort of interface, some sort of capability, some sort of structure that maybe our library doesn't provide natively. And so what I have here are what I call interface adapters. And these are a way of building up higher level functionality from lower level functionality which may exist. So something may exist natively, but we can also create this externally to the library. So as an example, let's say we want a tensor which exploits this point group symmetry. And as I said before, this is essentially a block sparse structure. So what we can do is we actually take the non-zero blocks from this tensor, and each one of those non-zero blocks is now dense. And so if we have a library that can do dense tensors, then all we have to do is do some logic to handle this guy as a collection of dense tensors, and now we have our sparse symmetric tensors. So we can add in capabilities that didn't exist already. And maybe this isn't the most efficient way to do it. Maybe it could be done more efficiently natively by another tensor library, but at least gives us a wider range of options. Again, here we could add 2 levels of capabilities here, hierarchically. And this is actually not a really crazy thing to do. This half of the slide actually is what exists in Aquarius right now on top of CTF. So this is a completely feasible thing to do. And getting back to what I said about in the very beginning about Laurie Burns' work with C4 and Sci4, another thing you can do is instead of having, for example, a library that you call that you can actually link into Aquarius and have an interface for and things, there's a lot of code out there, a lot of existing programs that are standalone, that don't expect to ever be used by anything else. But that doesn't mean we can't use them. It just means we have to be tricky about it. So out here in Aquarius, we could drop out and say, okay, we're going to take whatever we have so far, some tensors maybe, some integrals, some other things, and we're going to put these in a format which this program can understand. We're going to maybe prepare an input file or some sort of temporary files. And we can actually run the external program by itself, and we're going to trick this into computing exactly what we want it to compute, whether this be a whole calculation or a part of calculation or whatever. And then we can parse its output files, we can read the binary files, and convert these back to whatever format we need. And so now, unwittingly, this external program, which was never meant to work with other programs, has given us exactly the piece that we needed to keep going in our computation. And this can be stuck back into the marketplace. And so what I'm trying to get across here is that the pieces that the program uses to accomplish its end goals don't necessarily even have to be written to be interchangeable, to be modular, to be libraries, or to be used by other programs. If we're tricky about it, if we have enough inside knowledge of what this guy is going to do, we can trick code into helping us out to accomplish what we need to do. Okay, so I've talked a lot about sort of how Aquarius works, some future directions for the Aquarius to go to take. So what can Aquarius do actually right now? no one said anything, this is Sam Blau, who is also in the audience. So he's another CSGFer. We've been working recently on computing some singlet-triplet gaps of some OLED materials with equation of motion coupled cluster, so molecules like this guy. And this uses a variety of algorithms. It uses, at the various lowest level, the things I showed you before. It uses the SCF algorithms, the integral algorithms. It uses tensor algorithms very heavily. This uses iterative solvers, all sorts of things. Another example is some new coupled cluster approximations that we've rapidly developed and benchmarked. This is in collaboration with some European groups. The success story here is that I spent maybe a year implementing these in the legacy style, in the C4 package. That was the code we saw at the very beginning, where everything is explicitly laid out. I then spent a couple of months writing them in Aquarius. And it only took a couple of months because we had some bugs in the tensor library that we had to work out. Really, if I did this again, it would take maybe a week to implement all these methods. And they just work. And lastly, we have another type of calculation. These are coupled cluster singles, doubles, triples, Green's functions calculations on the uniform electron gas. Okay, implementing the uniform electron gas, that took an hour. Implementing the Green's functions took a couple days. And then we have code which can compute this. And I also implemented this in another package, and it took me between 6 months and a year. So not only is it extremely easy to write code to these types of interfaces, but these types of interfaces, when using capabilities, when made to be flexible and modular, can exist in one form, but use a lot of different algorithms. And this means not only that they are flexible now, but that they may be more future-proof in the future. So as new algorithms and architectures come along, maybe we have to add new capabilities, but the capabilities that are there work perfectly fine, and you can swap out what algorithms we use behind those. Okay, so to summarize, to make code work together, we have to have interfaces, right? Because one code has to call another. For that, you need an interface. But these interfaces can be independent objects. And they can be generic and flexible at the same time, because we can define them in terms of capabilities. But we don't want to take away opportunities for optimization. If a library has some awesome feature that we want to use, we want to make it available to use. We don't want to handicap all of our algorithms to some basic level. We want to be able to take advantage of anything and everything that our algorithms provide. And so defining new capabilities gives us a way to do that. Third, this is what I was hinting at with the Spot the CSGFer game, is that what you really need to do is go out and find people to collaborate with. On the few previous slides, there are collaborators from all over the world. And I can't really take credit for that. But I've been very fortunate and very honored to work with these people. And the work that I've done has been greatly improved by interaction with these kinds of people. And you don't even have to go through your advisor to find people. You can find people, perhaps even in this very room. Because there's a lot of excellent talent, and a lot of very great people here. And people here also know a lot of people that are very excellent, very, very smart. So I would encourage you to go out and find people to work with, find perhaps areas where you can apply your work, which isn't traditionally where it's applied, and to make some round peg or some square pegs fit into some round holes. So with that, I'd like to say thanks to everybody from CSGF who I've worked with closely, my advisor and my previous advisor, all of my external collaborators, and thank you to you. And I'd like to take any questions.